Shall we start out with calorimetry, our favorite topic of all time? So, looks like a couple of you wanted to go over some thermochem stuff, so why not start with calorimetry, everybody's favorite? So, let's go ahead and read this. We have 4.18 or 81 grams of benzene. Formula given. It burned in a bomb calorimeter. Total heat capacity is 7.922 kilojoules per degree Celsius. We have a temperature change, and we're asked what's the heat of combustion per mole of benzene, aka delta H. I guess let's go ahead and take a look. So this is kind of two people's questions at once. We'll go over some pure stoichiometry as well for Elizabeth, but this will kind of be some of the thermochemistry that we'll be able to cover today. And then looks like we're doing heats of formation as well. Maybe we'll do a Hess's law type thing as well if we have time. And then we'll go over some gas stuff, density. Oh, good. So she has asked about theoretical yield as well. So that's going to be good. That's also stoichiometry. So we're covering all our bases there. And then Kevin wants to do yet more solid stuff. Okay, cool. So let's go ahead and take a look here. So remember with bomb calorimeters, the Q of the reaction is just the total heat capacity times delta T, right? Because the mass for a bomb calorimeter is already included in the total heat capacity. So we're good. We can just work directly with this. So this is telling us that the Q for the reaction is just going to be our heat capacity times 9.88 degrees Celsius. That's going to be our delta T, right? Final minus initial. So if we do this fun stuff, we get 7.922 times 9.98. Doing that, we get negative 79.06 kilojoules. All right, and we know that this amount corresponds with this mass of benzene. So if we want it per mole of benzene, we're going to have to see the basic ratio between this and the moles that we have here. So that's just one more kind of step for us. Let's look up benzene's molar mass. I have completely made this problem up, so I don't know that the delta H will actually line up with what it should be, but it'll be close enough. Maybe. So doing this, we get 4.81 divided by 78.114. That is 0.06158 moles of benzene with 3 sig figs. And so our delta H is just our Q over the moles, right? So negative 79.06 divided by 0.06158 moles. And so 79.06 divided by all that crap. What did I do wrong here? Because I didn't put parentheses. That's better. Okay, so then I got negative 1284, actually, which should be rounded to negative 1280 kilojoules per mole, and that is our answer. Hooray! This is definitely way off from what it should be. Benzene actually is probably like twice as much as this, but That's what I get for making up numbers. So shame on me. So that is how we would do something with a bomb calorimeter. If we have a coffee cup calorimeter, we only have to include our mass and specific heat instead of total heat capacity. Other than that, it's all the same. All the same. So just one more term in that equation. So yeah, cool. And then to go from Q of reaction to delta H, we would use this sort of thing, depending on whatever moles you're asked for it. All right, so awesome. As always, if questions come up, go ahead and type them out. We'll see if we can go over more stuff. Let's go ahead and do some delta H reaction from heats of formation. So let's go ahead and see here. You know what? I should probably actually look up a thing for this because we're going to be looking up on the table, huh? Okay, one sec. Let me grab the textbook. Okay, let's take a look here, since these ones do have values that we actually need to look up. Creature, shut up. Okay, here's one. Let's do problem 71 from the book. I think you guys did this at homework a while ago. So we have 2 aluminum plus ferric oxide turns into aluminum oxide plus iron. So let's go ahead. We're gonna need all the we're gonna need to put all the we're gonna have to find up where all the thingies are on our lovely table, which remember on your exam you're going to be given the values in the problem, so you're not gonna actually have to look any up. But remember in Discord we did have that table that has all the heats of formation here. So for us right now, we're going to have to look it up. On your exam, you will not. Okay, so let's go ahead and look at all these things. So we have aluminum oxide there, as we can see. I'm just going to go ahead and write that one down. That's negative 1669.8 grams per mole. Let's see, what else do we have? We have iron oxide as well. Remember that elements in their natural state, like iron solid, is always 0. So we only need to look up things that are parts of compounds. So, and that one looks like it's going to be negative 22.2. Okay, back to the regular window, now that we have our values. So remember that delta H is kind of always the it's going to be the products minus reactants, right? So technically for this reaction, it would be we would have the delta H's for these ones, or rather the HFs, delta HFs for those, minus the one for iron oxide, iron 3 oxide, and 2 of the aluminums. All right, remember that these ones are 0 because they are in their normal state. So we just have to basically do the math here. So remember these guys are 0, so who cares about them? So that's going to say we need 1669.8 minus negative 882.2. Or actually, yeah, we're good. Do this fun stuff. I know how to calculate these, I hope. Negative 1669.8 plus 882.2. We get negative 787.6 kilojoules. So that would be the energy change associated with this, technically per mole because it's delta H, but let's just put it there. So you remember, for all your compounds, you're going to want to look up the values on that big old table. And then, or for us on the exam, it's just going to be given to us. But that's how you would do it. So you would go ahead and find all your compounds on that stuff, and then you would take the total heats of formation for your products and subtract the heats of formation of your reactants. And so remember, stuff by itself is 0, so you don't have to worry about that in its elemental form. Kevin, did I do the math wrong? 1669.8, 882.2. I think one of us may have done 828 instead of 882. It's possible that I copied the number wrong. Let's go ahead and let me just double check that. Double check yours in the meantime as well. 1669.8, an iron oxide. Fe2O3, 822.2, that's the problem. I copied the wrong number. So again, that should not be a problem on your thing, because the things will be given to you in the problem. As always, Kevin has found that I am incapable of copying numbers properly. Oh, and there we go, 847.6. And that's what Kevin got. That's awesome. Okay, so yes, there's your lesson. When you're looking at the chart, copy the numbers properly. Again, not a problem on our homework, though, or exam. Cool. So this is kind of the big thing here. Remember that if you have more than 1 in your reaction coefficients, you're going to want to multiply it by that. So technically we had 2 irons by themselves, iron solids, so we're going to have to multiply 2 times 0. Doesn't really change anything, but remember that you want to put your reaction coefficients there as well. Alrighty. Thermochemistry is fun. Okay, let's go back to questions that we had. Let's go ahead and do some stoichiometry next, so that we can get Elizabeth's things out of the way. In fact, let's see, I did a problem for the other class earlier. We can just use that. Save this for now. Go back. Alrighty. Let me just copy this one. Okay, back we go. Oh, yes. Oh my gosh, what? Sorry, I have to delete this 7 or else it's going to destroy everything. Okay, well, fine, whatever. Wait. Why is this being so silly? Please let me write on you. There we go. Okay, here's our question. All right. We can ignore the underlines here. We'll underline them again anyway. So again, this is right now for us, it is a multi-step problem. I'm trying to avoid that on your actual exam because not only would it take too long, but I don't want you to be like, oh, I mixed up the balancing and now the whole thing's off. Even though I know how to do all this limiting reactant stuff, I don't know how to balance an equation. I don't want to get you to lose points for something like that. So you'll lose points on the balancing questions, but not on the stoichiometry ones. But because this is review time, we can throw in all the things at once and cover all of our bases. So let's go ahead and... Wow, those planes have just been going all morning. What is going on? Let's take a look at the information we have here. We have our reactants here. That we're told, so we should probably come up with a chemical equation for them. we're given, it looks like, a mass of the first one, and then a volume and concentration for the second one. And we are asked what is the mass of the solid product, assuming 100% yield. Actually, for us, let's go ahead and let's do the theoretical, or the, here, let's say we have a different yield. Assuming 78.9% yield, because actually this should work without that. Well, whatever. Okay, there we go. I've changed the problem to throw in the percent yield type thing for us as well. Okay, so we've got to predict the products for this, right? Once you do so, you should get 2 sodium chlorides plus calcium sulfate. If we are to put in our states of matter, we're told that we're given aqueous calcium chloride and a mass of sodium sulfate. Masses mean pure substances. Sodium sulfate is an ionic compound. Ionic compounds are solid at room temperature. So that's where we get those. So looking at the products, we definitely have water present. So we're going to see that our sodium chloride will be aqueous, has sodium in it, has chloride in it. And the other one, the calcium sulfate, would be solid. And we're also told that it's a solid product in there, so that's a good thing that we do have a solid product. That is an indication that we've done something right. Cool. So with limiting reactants, we have to take a look at both reactants separately, and we're going to want to make sure that we choose the smallest number at the end there. So let's go ahead and do our sodium sulfate first. So we're given 3.24 grams sodium sulfate. Oh gosh. Well, we'll figure this out in a sec. We'll have our molar mass for sodium sulfate. We'll now have our reaction coefficients. And for calcium sulfate, I still have this up, so it's 136.14. That's 142.4, okay. Okay, 05, I guess Kevin gets, whatever, close enough. Let's do the math. So 3.24 divided by 142.04 times 136.14. We get 3.105 grams of calcium sulfate. If we're looking at the second one, we're given a volume and a molarity. Remember, volume is our measured quantity. Molarity is a conversion factor. And since molarity is per liter, I'm just going to go ahead and convert this milliliters into liters right away. Should not be something problematic. I hope by now you guys can do milliliters to liters without any problems. And this is, of course, the calcium chloride. So notice, again, the second half of our unit conversion here is identical. The only thing that changes how we get our moles of our reactants. Remember, there's 3 ways we could do it. We could have a mass, which would be a pure substance. We could have a volume of solution, or we could have gas quantities as well. So we could have pressure, volume, temperature of a gas, and solve moles from that as well. 2821 times 0.25 times 136.14 is 0.9601 grams. So looking at these numbers, this is our smaller one, right? That's the one that we're going to choose as our theoretical yield. And remember, the theoretical yield comes from the limiting reactant. So if I were to ask you which one is the limiting reactant, you would say it's calcium chloride. However, since this question asked, we're essentially asking how much is produced, and we're given a reaction yield. We're asked for the actual yield here. So remember that percent yield is the actual over the theoretical. And percent, throw that in there. So our actual yield for this problem would be 0.9601 grams times 78.9%. .789. And so our real yield would be, this is what our final answer would be there. Wow, so look at how much crap we were able to cover with one problem. So we not only predicted the products of our equations, we balanced it, we did our states of matter, we then did our limiting reactant stuff, and then we did our percent yield. So we have a ton of information from this problem for our review purposes, but again, I would really be only asking you like kind of one thing at a time. Because I don't want you to get hung up on, oops, I balanced it improperly and now the whole thing is wrong. So yeah. All right, cool. Any questions on that one? I know we have, here, let's see. I wonder if this would make anything better. Can we even fit all of this on one page? Yeah, we can. Look at that. Go figure. Okay, so all this craziness on one page here. So we have the problem. Look at all this crap we were able to do with it, and we got our actual yield at the end there. So if there are any questions on that stuff, I'm happy to take a look at them. Okay, well, then back to horizontal view we go. Just remember stoichiometry, and I think we're good there. Okay, so let's take a look. Hopefully, Elizabeth, that's kind of what you were looking for with the stoichiometry problem. And let's go ahead and back to our review. Okay, so next question we had was a partial pressure from known gas moles to unknown pressure of other gas. Okay, we could do this. I think what I'm understanding here is, let's see. To unknown pressure, okay. Of neon, argon, and helium has a total pressure of 6.74 atmospheres. Contains 16 grams of neon, 22 grams of argon, and 3.8 grams of helium. What is... Actually, I think what she's saying is slightly different. Except let me put those the correct way. Oh my gosh. Calm down, tablet. Okay. Okay, there we go. I think this is the kind of thing she's looking for. Where we're given the partial pressure of one gas within a mixture, and we're trying to find the partial pressure of a different gas in that mixture. So, remember that gas mixtures are all about essentially the ratio of pressure to moles, right? So let's go ahead and convert these into moles so that we can have everything in units that we can deal with. So 16 grams of neon. Let's find out what neon's, oops, don't need that. Neon's atomic mass, oh, go away, is 20.18. So 16 divided by 20.18, 0.7929 moles. And then the helium is 4.003. 3.8 divided by 4.003. 0.9493 moles. So already we should be expecting to have, we should expect to have more pressure of helium, right? So Kevin, we actually will not need the moles of argon here. Not terribly necessary. Since we know these are at the same conditions, we know that the volume and temperature for this mixture is the same throughout, right? So we're really just comparing pressure in moles. So this is telling us, this problem is telling us that we know the pressure of neon is related to the moles of neon. And so we know that at these conditions we should have the same ratios, basically, because the volume and temperature and R are all the same. So let me make this a capital N down here, just so we're all sure about this. Yes, you could technically do the total pressure and then solve for the partial pressure of helium after. That would totally work, but we can kind of bypass that if we want, since we're just essentially using our kind of combined gas law here. So the pressure of neon was 6.74 atmospheres. And 0.7929 moles. Remember, thankfully, again, because the identity of a gas does not matter when we're using the ideal gas law like this, we can just say, if this amount of moles gives this much pressure, then this amount of moles must give the other type of pressure. So it's just a proportion problem. So let's go ahead and solve for it. 6.74 times 0.9493 divided by 0.7929. And we get the partial pressure of helium to be 8.0, actually let's say 8.1 atmospheres with 2 sig figs. I believe, Kevin, you should get the same thing if you try for the whole pressure and the total number of moles. You should get the same answer. using your mole fraction. So either way, it should work. So, hooray. So remember, our combined gas law, while moles is not usually included, we can say that, V and T are equal. Let's just compare the two this way. However, of course, if you did know the total pressure, and I did give you that as the problem, you would definitely need to calculate the mole fraction first by looking at all of the moles put together. So, but because it looks like she had asked from known gas moles to, okay, well, I don't know. Whatever. This is a good way to do it. If the total pressure was 6. If this was the case, then yeah, let's go ahead and add them all up. So we know that the N total would be 0.7929. And Kevin has done argon for us, 0.551. 0.9493. And actually, let's find this. Let's go ahead and calculate this. 0.7929 plus 0.551 plus 0.9493. We have a total of 2.2932 moles. So for mole fraction of helium, that's 0.9493 over 2.2932. So that's mole fraction of 0.4140. And then we could multiply that by this. So partial pressure of helium is total pressure times mole fraction. And so we can go ahead and do this. Multiply that by 6.74. And so now we get the partial pressure is 2.79 atmospheres. Hooray. Though it looks like we need proper sig figs as always. And so that's what we would get. Slightly less than half. Yeah, that makes sense. Okay. Hooray. So I guess two ways to work with these sorts of partial pressures. So we can just use the combined gas law to do it. Compare two partial pressures directly if we already know their moles. Makes things easy. Or if we had the total pressure, we could use our mole fraction, which we would get by comparing the moles of one of our gases versus comparing or adding them all up together. And then we would remember that partial pressure is total pressure times mole fraction. Hooray! Okay, so hopefully that answered that. Density. All right. I'm not sure if this is about density of a gas or density of as used as a conversion factor. So I guess we'll do both. What is the volume? No, mass of... No, volume. I want volume. I have a 282.4 gram sample of gold. Density is 19.1 grams per mil. So density is just a unit conversion factor. Nothing new here. Always start with your measured quantity. Measured quantities have 1 unit. And then we're going to want to put our grams on the bottom, milliliters on the top. And hooray, we can go ahead and calculate it. 282.4 divided by 19.1. We get that the volume is 14.79 ml. I guess we'll need 3 sig figs, so 14.8 ml. Hooray! Remember that that's the same thing as a cubic centimeter. Doesn't matter which unit. I guess in this case we're not even given a unit that we're looking for, but you would be able to convert that unit depending on what you had. So cool. Hooray. Okay, so for density of a gas, remember this is related to the molar mass, right? So let's see, what is the density of, what's our favorite gas? How about argon? At 2.14 atmospheres and 50 degrees Celsius. So we are not at the beach today with our, well, this time we have a non-toxic gas, so go figure, now we're not at the beach. But there we go. Let's see, what else are we gonna need here? No, that's it. So, we have a formula, right, for molar mass with the density, right? So density is it is going to be, I can remember this, molar mass times pressure over RT. Kevin will correct me if I'm wrong. Let me make this a happier squiggly M. Cool. Okay, good. So argon has a molar mass of, don't remember, don't need Discord right now. Oh my goodness. Periodic table, there we go. Argon. 39.95. It's like an infomercial. 39.95. Woo. Pressure is 2.14. R. And then the temperature is 50, which we are going to have to add 273 to. So that is 323.15. I hope. Yes, that's how we do math. Okay, cool. Plug all this stuff in. Times 2.14 divided by 0.08206 divided by 323.15. Doing all this. Apparently I get 3.22 grams per liter. Hooray! Remember, this formula will give you grams per liter. Technically, I should put the units in, but let's go ahead and see. Remember, this is grams per mole. This is atmospheres. This is liter atmosphere per Kelvin mole. And here's Kelvin. So Kelvins will cancel. Atmospheres cancel. Moles cancels. We're left with grams per liter. Hooray. All right, so density of a gas, we just use that formula. And that's it. So hooray. Yeah, that'll be it technically. So we've done it. Lucky us. We have done theoretical yield. Okay, so Kevin wants to do more solid stuff. All right, so really the solid stuff that we want to focus on, there's really two topics that we want to focus on with solids. So focus on classification and focus on band theory. So classification, remember that's types and then like kind of forces that are holding them together. And band theory is talking about, conductivity and band gaps, that sort of thing. So this is all I care about with solids. So, you're not going to have to do your unit cell geometry and take 30 minutes to do one problem. So don't worry about that. Focus on these things. So let's do, I guess, one of each. Let's see. How about... Okay, here's a question for us. So here's phenol, which is given a formula for us right there. We're going to be, let's go ahead and classify it and see what type of bonds hold it together. So remember our 4 types of solids. We have metallic solids. We have molecular solids. We have network solids, and we have ionic solids. So, based on what we would know about this, what type of solid do we think phenol is going to be? I mean, hopefully there's a couple we can get rid of right away. Definitely it's a molecular solid, right? I mean, there's no way it's metallic, right? There's not even a metal in there. There's no ions happening, so those 2 can go away. Remember, networks are kind of like you would have to know that they're networks. So something that would be a network solid would be like a diamond or glass or graphite, things that have the same kind of connections over and over and over again. And so networks, I mean, you would... it would say something that would tell you it's a network. Yes, and indeed, yeah. So we're held together by intermolecular forces, and Kevin is right. We're going to have some hydrogen bonds in there going on because we have the OH group. All right, and just to recap here, the forces here, we have metallic bonding. We have IMFs. We have covalent bonds. So your polymers would also be network solids because they are just bonded and bonded forever. And then these would be just electrostatics. So correlate these and hopefully be able to classify something as something else. There's one other type of classification we have that any of these can go through. Oh gosh. Any of these solids can be classified as crystalline or amorphous. This is typically talking about molecular and network solids because ionic and metallic solids are pretty much always crystalline. Here are some let's do this and then we'll get back to your question, Tyler. So, something crystalline. Remember the difference between a crystalline and amorphous solid is this is kind of like organized and regular, and they have unit cells, and this is just kind of random, disorganized, and these would not have unit cells, right? Because unit cells are repeating patterns. So yeah, there we go. So what would network solids look like? Well, here's one. That is a network solid. Here's another one. Lovely. Um, how would I have given polymers to you? That's a question. Um, ah, a polymer would be a network solid as well. And you can throw in whatever word you want in here: propylene, whatever, polyethylene, whatever, those sorts of things. If you see the word poly in front of it, that's a polymer. And polymers would be our network solids. So, glass would be another one. So remember, glass is silicon and oxygen going around and blah, blah, blah. Fun stuff. I can't draw these. These are just awful. Let's just get that away from here. Yeah, so that would be a network as well. Cool. Those are kind of how you would identify stuff as a network. They're the kind of there's not many of them. Let's just say that. So, chances are, if something is covalent, you're looking at a molecular solid. Yes. So, if we look at phenol, we can see there are 13 atoms. 13 atoms a network does not make. Networks have millions of atoms, so where they're all connected together. But this one, if we draw the structure for phenol, which you do not have to, this is what phenol looks like. If we have another phenol molecule, these are not covalently bonded together, these two molecules. So network solids are one giant molecule, where you're going to have molar masses that are in the thousands, tens of thousands, hundreds of thousands. This has a molecular weight in the low hundreds, so not a network solid here. So because we can identify discrete molecules here, it's going to be a molecular solid. So that's kind of how we're going to know. I guess we can talk about some properties too. Hopefully you guys know properties of metals by now: conductive, shiny, ductile, malleable, all that fun stuff. Molecular solids, just so we know, they're often brittle, non-conductive, non-ductive, apparently. Let's try that again. Non-conductive. They're also got low melting points, relatively speaking. That's like the fourth time that plane has gone by. What is going on? Wow. Here, let's... Alright, microphone back on. I know, what is happening here? War in Ridgecrest, of all places, really? Middle of nowhere. Okay, network solids are also gonna be brittle and non-conductive. But these melting points can be kind of all over the place. It just depends on how big the network is. Like a big old diamond would have a different, depends how perfect the crystal structure is. So let's not worry about melting points there. Ionic ones are typically, and molecular ones are also typically white. Most often, unless they've got a bunch of nitrogens in there or something. Very often molecular solids are white. Think of sugar, think of ice, think of I don't know, phenol. These are all kind of whitish crystals. So there we go. These can be colorful. These are typically have very high melting points, in the thousands of degrees Celsius. So sodium chloride melts at 3,000 degrees Celsius. These would be conductive when dissolved. Remember, ionic solids would, if they're going to dissolve, they would conduct electricity. Um, so, yeah, just some other stuff about these solids, I guess. Cool. Okay. I don't know what else. Oh, we can do some band stuff, I guess. Okay. Remember, bands. Band. Remember, like before, we have conductors, semiconductor, and insulator. Small gap, big gap. Hooray. Remember, conductors, we have nice overlap here between our two bands. Let's see. It's all about the band gap. Let's see, what else do we have? Remember, semiconductors have some cool things that with semiconductors you can have the size that affects band gap. Do you remember we talked about quantum dots? And then we also have like kind of temperature effects as well. So remember, small stuff had those larger band gaps. We got the bluer colors out of those quantum dots. And we had the, the redder side of things with the larger quantum dots. So remember that with semiconductors, because they have this kind of small band gap, we can see very easily that kind of trend between size and band gap with semiconductors. Insulators are pretty much always going to insulate. Conductors are always going to conduct. It's the semiconductors that have the interesting properties. So, and then as Shane is going to throw in superconductors again, which we're not going to worry about. Yeah. Okay, so there's our band theory. Remember that these bands are just giant MO diagrams because there's so many atoms and molecules in here where they just start overlapping. So, yeah. All right. Let's see. Anything else? No, that's it for solids. Who cares about the rest? Thankfully, I've written the exam, so I can tell you, don't worry about the rest. So, cool. There's all our solids. Hooray. All right. So, Kevin, hopefully this answered that question. Okay, I think we have gotten through all of the topics that were listed there. So, cool. With that in mind, let's see. So, about your exam. Oh, I can just tell you. So you have this is the breakdown of your questions. 10 gas questions, 10 IMF questions, 4 questions on solids, 26 on everything else in the semester. Again, roughly evenly split. With the other 9 chapters. Roughly. So most of them would have about 3 questions. I think chapter 1 only has 2 because chapter 1 is just trash. And so the rest are kind of just evenly taken from the rest of them. So that is 50 total. 150 minutes. We have a unit conversion factor here of 3 minutes per question, roughly speaking. So, because as always you'll have access to all of them at once, it may be worth it to kind of flag certain questions as this one's going to take me a bit of time. I should save that to the end and focus on getting as many of the easy ones out of the way first, so I can really save more time for the harder questions. So as always, this is a mix of conceptual stuff and calculation stuff. The conceptual ones presumably will take less time. It's going to be like, what type of solid is this? Hopefully that'll take you 30 seconds or less, and therefore you'll have another 2.5 minutes to dump onto another question or something. So it should all work out nicely for you guys. Oh, I have an extra credit thing for you guys. I guess I'll just tell you now and go off topic. So the extra credit thing is just going to be a survey, like 15 minutes. It is going to just focus on the class in general, like how you thought things went. Did you find Discord to be useful? Did you, completely hate the group project? Did you, if you were to compare this with other online classes, what strengths or weaknesses does it have? Blah, blah, blah. So, that'll be that thing. It should only be a few minutes. I'll probably give you guys until Friday to take that. I'll put a link on Canvas for you guys. Free points. So, hooray. And let's see. What else? Since most of your group projects I had seen already, the grading on those should be pretty quick, at least for the group parts. The individual parts will take more time because I'm going to have to read Kevin's paragraphs on how Tyler was the worst partner in the history of partners. I think Kevin had submitted about a 7-page essay on that, so I have to go through all those. I think at this point I've graded most of your homeworks. There's probably 2 or 3 that are left over, plus those pesky post-exam ones that we'll see. At some point I may be like, you did it, you get full credit. So we'll see. So I will probably put your grades in on Friday, so you'll know. Everything will be on Canvas, and I will once I have all the grades in, I will tell Canvas what the grade cutoffs are going to be, so you'll be able to see the letter there. I don't know how quickly it'll post to my bandweb for you guys, so at least you'll see it on Canvas. Anything else there? No, I think that's it. So, okay. Any other questions on the final exam itself? This should be a pretty handy little guide here. So again, it is mostly focused on the recent stuff, and then the rest is from all over the place. And I've avoided super long problems because I don't want you to do that. So, of course, with 3 questions per chapter, all of these chapters have obviously way more than 3 topics within them, but, that's the roulette of the game, right? You're going to probably focus everything onto bomb calorimetry, and then there's not a bomb calorimeter problem, and then that's just the worst, right? So, I apologize for that, but obviously I can't give you one question on every topic because that would take 10 hours then or more. So yes, I hope what you study for is on the exam, but we know the memes are going to be not showing that. You have until, I guess, Wednesday at 11:59 p.m. So technically not Thursday. So it'll open midnight tomorrow, aka 13 hours from now. And then it'll close 48 hours after that. So any time on Tuesday and Wednesday, you can take it. You have to do it in one sitting because I don't think your timer will stop. So you can't say I'm going to do an hour here and then another hour and a half here. Not going to work. As always, I have no control over your books and stuff and the rampant cheating, but such is life, COVID times. Yeah, cool. For the survey thing, you'll have till Friday, though. But the earlier you do that, the better. Yeah. If that happens again, yeah, because that sucked yesterday, right? Or Saturday. That was no fun. So if there are problems, of course, we'll make the necessary adjustments. But so your exam does have a few number of pictures, by the way, also like graphs and charts and Lewis structures. So if you guys had problems with that last time and you were able to find your workarounds to doing that, make sure you have those workarounds handy. So I think some people like were using a different browser or something and it wouldn't display the graphs properly. Um, Whatever changes you made last time to make it work, um, try and have that there for you. Um, Again, if you are encountering a problem like that, send me a message on Discord, ping me, or DM me, and then move on. So don't like I'll try and respond as soon as I can, but you know, it would probably just be best to skip to the next one so you're not just wasting time waiting for me. And what I'll try and do is just message you the graph or picture in question. Um, so yeah, that should work. Yeah, but hopefully everything will work nicely and it'll all display properly, and then we won't even have these problems. So cool. However, of course, if you're pinging me at 3 in the morning because that's when you decided to take your exam, I probably will not be awake. So, yeah. All right, we did it. Congratulations, everyone. You have survived Chem 111. I will see some of you in 113 in the spring, in January. And who knows, maybe the rest of you in OChem next year or never again. So, whichever way, it all works out. So, with that, I guess good luck on your exam tomorrow and Wednesday. Good luck on your other courses exams, or whatever things you have left to do for those. And then, have a nice holiday break. Once you finish your exam, treat yourself. You've earned it. It's been a lot of work for you guys, so definitely treat yourself. Yet, definitely happy holidays. Enjoy the freezing weather of Ridgecrest or Tehachapi or wherever you're having fun. And, be safe over the holidays, of course. And hopefully, a vaccine will come out real soon and then we can get back together in this next fall or something. So, and have real class with real lab and exciting stuff. So, alrighty. Well, I guess that's it then. So, take care, everyone. Good luck tomorrow.